So when I went to the US to study, I had a very clear idea that I'm going to return. I never anticipated the coming of the desktop, and then the fact that you can have such a powerful computing device in your palm. None of this I anticipated. So the opportunity wise from an individual's point of view, I think is probably never been better than it is today in this field. See, around 93, we launched our own national conference so that students could also come and meet. And that conference continues. The National Conference on Communications continues till today.
This is the Professor Mahesh Podcast. I am Mahesh Panchagnula from IIT Madras. This podcast is your resource to bring you information in a simplified fashion that will allow you to make informed career decisions. We dissect global trends and present it with an Indian relevance added. This podcast is supported by IITM Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global is the platform that takes our startups, our thinking, our teaching, and our research to the world outside India. Today, we are very fortunate, and I'm personally excited and honored to have as our guest Professor Bhaskar Ramamurthi, our former director and Zoho chair professor and institute professor at IIT Madras. Welcome, Professor Bhaskar. Professor Bhaskar, in his tenure as the director of IIT Madras, started an exceptional number of path-breaking new ideas and brought a new paradigm of thinking, which is continuing to bear fruit even today. The fact that we are ranked very highly in NIRF is a result of many of the initiatives that were put in place as a result of his vision and his effort. Welcome again, Professor Bhaskar. Thank you very much for making time. Let us begin with your own career. You swam upstream when it was not fashionable. You went abroad, did your PhD, and came back to become a faculty member at IIT Madras. Can you describe the thought process that went into that aspect of your career?
So when I was studying here at IIT Madras, actually when I joined IIT, I had no idea what engineering was about or anything. Some classmates in school told me I should write IIT entrance exam because I was studying well, and I wrote it and I came. I really had no idea. In fact, my father, as the fallback, had just arranged for me to ensure that I got admission into Loyola College for BSc. It was no plan. There was no plan that if I don't get into IIT, I'll go to NIT. There was nobody. I mean, my dad also didn't seem to have much of a feel for what I should do. Anyway, I got into IIT, and I didn't know what IIT was. It was 5 years, so I never thought about what next. Just went on with the flow. But here, the teachers were people who worried about you. Some of the teachers, they thought about what you should do and so on, observed you. So some of my teachers put the idea into my head that I should actually study further and become an academic. I never thought of that. I didn't even know what it entailed. But they actually told me that I should try to go abroad to study because the opportunities for higher studies in India at that time were much less, and they suggested this to me. But they also told me that I should aim to return. Not because already there were many people, large part of the class at that time in the late 70s and 80s was going abroad and remain. And it was already becoming clear to my teachers that they were all not coming back. So they told me I should do that. And I took that seriously for some reason. So when I went to the US to study, I had a very clear idea that I'm going to return. And in fact, they even suggested to me not to get into disciplines where it's impossible to come back or very difficult to come back because the very minimum you require for an academic research and so on, equipment-wise and lab-wise, is not available here. So they said, you please, don't get into microelectronics and these things because they also didn't have any vision that India would even advance to the extent it has. They assumed it would be pretty much what it was like in those days. And they said, look, go for things that are more analytical, more. And in that time, in the electrical engineering department, the high points were actually the classical area of networks and the fairly at that time hot area of electronics. But it turned out that they told me that one was obviously mature and reaching sunset, one area, and the electronics was pretty strong. But they told me even this will, by the time you get going, it will be very mature. Why don't you get into communications or things like that? That was their suggestion. I really didn't know much about, except what I was taught. So then I said, okay, so that's how I got into the study of signal processing and communication. There was one faculty member in the department at that time who was in these areas. So Professor Venkat Rao, he guided me to some extent. There were not too many courses being offered in these subjects, but project I did with him. And then I went to the US and studied these subjects. It turned out the advisor whom I worked under had switched. He was a person of wide capability. He had been in Bell Labs just before he joined the university, and he had moved from communications to, communications as in communicating between 2 points, to this emerging area where you try to compress audio and video signals, which is now, of course, we are all using all the time casually, MP3 and MPEG and all that. All this didn't exist, but the precursors of that. He had moved into that subject, and he told me, why don't you work in this for PhD? And I did so. It was, at those days, it was the beginnings of compute-intensive approach to these things. And we worked on mainframes or mini computers. There were no desktops in those days. Apple had just come out with the Macintosh during my PhD. There were no desktops, and even that field seemed to me to be something where I would have a dead end if I came back to India, because I knew IIT had a computer, but it was a very different kind, and I couldn't see where it was heading. So I actually told my advisor at the end of my PhD that, look, I want to switch. I want to switch to wireless to communications. Because I knew that in India, we were going to build wireless systems, at least for defense. Even I could not foresee that it will become such a commercial and such a common thing in everybody's hands in the form of cell phones. Cell phones itself hadn't been invented at that time. Just about.
We're still talking mid-80s in some way.
Early 80s.
Early 80s.
In fact, America had come up with the cell phone system, but it was very nascent, and GSM hadn't yet happened, and so on. So I said, okay, I'll work in. So I told him, look, for my postdoc, I want to go to a place where I can do wireless communications, which I had only learnt as a subject. I hadn't worked on. Fortunately, because of his past, having worked in many of these things, he actually connected me to a mentor in Bell Labs who liked people who switched fields. He had some thing about that. So he said, I like your idea, so you come. So I joined this group, and it was actually a continuation of learning, because he told me, you do whatever you want. You learn, you work with any groups. There were 3 or 4 different teams that were working there on different things. He says, you can choose and move from one to the other. And he gave me complete freedom to learn. So I actually worked 6 months at a time with each of those groups and learned completely new aspects of wireless communications from them, including what later on became packet communication, Wi-Fi, and so on. The beginnings of Wi-Fi was happening in that group at that time. There was no name for it, but... and I did all that in 6-month packets, 6-month chunks, about 18 months. Then I wanted to come back. So actually, I wanted a 2-year plan, but I came back after 18 months, and I got into IIT Madras as a visiting faculty member and waited for the advertisement to get regularized. And that's how I came here. And after I came here, I plunged into teaching, because my former teacher who introduced me to these subjects was teaching alone. There was no faculty member who was teaching these subjects. So he said, now that you have come back, let's do it together. So the two of us, went hammer and tongs, and we used to teach 2 courses every semester, non-stop. From a menu of about 8 or 10 courses that we used to alternate. And that's how we were both teaching for almost 10 years.
This was a time when even landline telephony had not penetrated.
Very little was there in India. And I wanted to... There was no question of actually using wireless for telephony was not even thought of, except police and so on. And then in 88, I remember very clearly, a gentleman who had taken over as the... Telecom was still completely as a government department. Okay. There was no BSNL also. It was all DOT. And research was also done only in DOT at that time, whatever research was done. And he actually became the head of that research center, and he came to, he was an alumnus of Institute of Science. He came to all the IITs and IISc, and he said, I want to sponsor research in your institution. The first, for them, it was a big move, actually do something outside of their department. And he said, I'm willing to support. And it was in the faculty meeting, and he came, and I put up my hand and I said, I want to build something. I'd never built anything in my life. Even in Bell Labs, it was just another academic type of environment. And he said, okay, and this idea was beginning that you could use wireless to actually, as part of the telecom network, not even to go to the subscriber, to actually between exchanges. And we wanted to build a digital system of that kind. And he actually funded it fairly generously at that time. For a young assistant professor, for a funding to an academic institution, which they were not doing till then, going back and looking at the value of the rupee at that time, it was a very, very big project. I don't know how he gave it to me. I had no credentials to on doing anything like that. So we started building stuff, learning how to build through that project. It actually worked. In 1992, we deployed, it worked. Then we transferred. It was in modern terminology, the TRL level that we worked was something like 5. We handed it over to CDOT, and CDOT took it all the way to 8 or 9, and then handed it to ITI. By the time it came to that stage, cellular technology had burst into the thing. So it was clear that what we had done was going to die. Then in the meantime, based on what we did, actually an American company, an MNC, approached us saying that we make chips, we want somebody to make a system, we'll fund you, will you do it? So actually the very next project, which was a wireless local loop, which is actually using wireless to go to the home, was conceived by us and was funded completely by an American company. It was not funded by government. At that time, for an IIT to get a funding of $250,000 to start with, ultimately it went up to $1 million completely from outside, was quite unheard of. It also gave us the freedom to, we knew we couldn't do it just with faculty and students. So we actually got some of the people who had worked on the earlier project and even some other projects before that, Professor Junjunwala and I, together, we had teamed up. So his projects also. We actually called some of them had joined CDOT, and there were very few avenues for employment in those days. So we told them, look, would you like to start a company? Because the American company that funded us, Analog Devices, was willing to fund part of the money to a startup. The word startup was not known, but so these students of ours, former students, formed a company, and part of the funding went to them. Part of the funding came to IIT. But we all worked in IIT in one place. So whatever is now considered very common, which is have a startup, work with startup and so on, we did that without having the terminology. Of course, the faculty, there was no policy of allowing faculty to be part of the startup in those days. So we had nothing to do with the company. And even the money didn't go through IIT. But we were able to get those kind of trained people, professional people into the effort. And that wireless local loop technology was commercialized, was deployed globally, actually, about 1.5 million lines in all, including about half in India. Then, of course, at this time when we developed this system, we actually had engineers building things, commercial level grade products and so on. Cell phones were still appeared to be expensive devices meant only for those who need it and can afford it. At that time, even incoming calls used to be charged in the cell phones.
Sure.
It was not what it is today. But then it became clear that due to Moore's law, cell phones will become actually cheaper than landlines and would actually replace landlines. And our technology, wireless technology, was actually a lower cost and faster deployable, in a much faster fashion, wireless technology to replace landlines. But it was still fixed phones in homes and offices. This one allows you to carry your phone wherever you went. So we knew that would take over. So that technology also sunsetted. And so this is how if you ask about me, I sort of took quite a few decisions which could have gone either way. I left an area which became very important later. MP3 and all have become the mainstay. But at that time, I felt it was not something that is going to take off, or at least require the kind of resources that we would not have in India and so on. I never anticipated the coming of the desktop, and then the fact that you can have such a powerful computing device in your palm. None of this I anticipated. So what I thought was not going to be feasible or not going to be useful or not going to be feasible in India actually turned out to be completely the opposite. So I left that area. Of course, I still know it well, but I left it. and I got into wireless.
This whole electrical engineering and what is sometimes popularly called circuit branches have a unique trait in that a faculty member like you or even a professional practicing engineer may give birth to a technology and will is also cursed to see the death of that technology in some sense, right? Mechanical engineers like me don't we can actually make a career living on one technology. How do you reconcile to that fact that even while you're working on something you may actually see the end of it?
Yeah. So that is certainly the half life of technologies, or even successful technologies that's become mature and sort of reach a certain saturation level in a matter of 10-15 years,
Yeah.
and some things actually get replaced with others. And this is very much true. And well, you have to. So the thing about and it's now becoming true of many things. But the thing is, you have to therefore focus on understanding things at a fundamental, basic, foundational level. Those things never change, and then you have to keep learning the super the layer on top of it. You have to keep learning where as things change, and you have to keep adapting to it.
Let's talk about your core expertise. Wireless communications. India has built its own 4G stack, and now the 5G stack is also been rolled out. Tell us a little bit about India's journey in this NG space, so to say.
So this. If you come to telecom itself, modern telecommunications, digital telecommunications, where because till the 70s, digital telephony had come in the 60s and early 70s all over the world, but a lot of communications was still what you would call analog. You're essentially sending speech, or later some data from one end to another. Bits you convert it to some kind of an analog waveform. You send it out across the other end. They receive it. Either they play it either they consume it as an analog waveform, or they detect the data from it and store it and so on using modems and stuff like that. This is how it was. The whole digitization of the network, ultimately leading to the internet, all this happened at breakneck speed and evolution in mid 70s to 2000. And then, of course, these ubiquitous wireless cell phones became very cheap, but the core ideas of cell phone technology had developed by 2000. Okay? It was only that became a mass product and became very fast in terms of the speeds, and therefore you could do broadband, and the devices became very powerful. You didn't need a laptop even, you could manage the phone. All of this happened beyond 2000, but pretty much the foundation was set before that. This whole thing, when it happened, we were left behind in India. Because for one thing, we had taken a route. The foundational technologies for implementing all of this is electronics. And even in electronics, we had taken a route which was very debilitating. Very strict import controls, and it's complete, therefore, strangulation of any attempt to grow these fields. In fact, when we did this project, which I mentioned to you, the rules of the country were such that to import, we didn't even know how semiconductor chips were made, forget about making them. And yet, to import every chip that went into this technology, into these systems, we had to get what's called a Not Made in India clearance.
Wow.
NMI. So we actually had to send it to a ministry in Delhi every time you imported a chip. And the only reason the IITs were able to even build and do projects was we had enough resources to send a person from the institute every month with all these papers to Delhi, get it signed and bring it back. Otherwise, it will take months. So that was the strangulation. So basically, in fact, Mr. Pitroda at that time had made a very famous remark that because he had built CDOT, he said whatever progress we've had in electronics in India is due to the smugglers. Okay, because you could buy smuggled products in the market. Okay, anyway, that was it sort of had some ring of truth to it. So anyway, the point is the electronics. That's what had happened, and so when we had to, and I think it was true in the military sphere also. We were making some radars and so on in LRD, not too bad. But beyond that, I think it had an impact even in military communications and everything. We were not making too many things. So, in fact, the Ministry of Education did a very interesting thing in '87. They got, the basic foundational courses that are important for communications itself were not even being taught. The texts that were used in engineering colleges were one generation earlier. It was all still related to telegraphy. Even we were taught telegraphy courses in IIT in 1977, 78. Okay, I think Kanpur IIT, for example, had already gone ahead, but not here. So, the ministry actually created a national program called Telematics joint Telematics program, because no IIT had, even most IITs had one or two at best people who were aware of the modern trends. Kharagpur, incidentally, though, many of them were completely homegrown people, had a pretty good grasp of this. So they actually got us to join together, five IITs initially, and then 6 IISc, to form this program. And every summer and winter, every 6 months, to conduct a 2-week intensive course for teachers in all the other institutions. They would come to one of the IITs by rotation, and we would conduct this course on we would cover all the important subjects to some extent, but take one topic and do it almost at a full course.
Audience were all teachers.
And it was also open to some people from industry. Industry in those days just meant Bharat Electronics, ECIL, and all that. And they would come, some 30, 40, and we'd run this program. We were given money to set up new labs so that they could be familiarized. Many of us actually took up the development of low-cost laboratory trainers, which then went to those colleges. I remember building one for digital communications. Junjunwala built one for fiber optics. Timothy Gonzalez built one for networking. So, it used to cost 30, 40, 50,000 rupees per bench you could have. And otherwise, we'd all used to import one bench worth of stuff from somewhere in England, and then everybody would just see it, because you can't nobody
play
can
with it.
Yeah. So we actually built all this. So a lot of this stuff went on. That the main thing about that program also is it created a community. We all knew each other. We could meet once in 6 months. In those days, you couldn't otherwise meet. So this community of telecommunications faculty formed in the country. And it was a very well-knit community. Around 93, we launched our own national conference, so that students could also come and meet. And that conference continues. The National Conference on Communications continues till today. And and we made it a national conference and not an international conference. We actually put it during the semester in about February timeframe, because we didn't want the headache of running it in a hotel and so on. We wanted to run it in one of the campuses. We knew that guest house, everything is available only off season. So we ran it like that. Yes, foreigners, even Indians from abroad, don't find it easy to come. But we said there are other conferences for that.
Sure.
So we focused on this. It has become a very good conference, and we built this community. That program was run for actually two 5-year stints before the government said, okay, now we don't need it. And but that community continues, and in fact, the importance of building such, and the collateral benefits of building such communities, you can see so many IIT directors have come from that. Deputy directors and directors, starting with Professor Faruqi, Professor Sinha, then the Sahasrabudhe, Surinder Prasad, Anurag Kumar, myself, Junjunwala didn't become a director, but he built a research park. Now Devendra Jalihal, Uday Desai, Abhay Karandikar, all of them are part of the Telematics group. What it did, it opened our eyes to what you could do together, to how you go beyond your narrow academics. So that's all it did, and it created the leaders. We didn't focus on this. We had no idea any of us were going to run institutions or anything, but it shows the importance of such programs. If you look at the total amount of money spent on that program, probably it was not much. So that was a MHRD initiative, actually, not a Ministry of Electronics initiative. And we called it the Joint Telematics Group. We actually even intervened with government with policy, written policy papers saying that, how do you push indigenization and so on. And really, we just gave it to the Planning Commission, just left it at that. We did a lot of that kind of thing. So that is how slowly, I think the generational shift in what is being taught, even in the engineering college system, everything improved. And these fundamental subjects started being taught everywhere.
Sure.
And in the IITs, of course, it went further. And then I think the real big change happened beyond 2010, when startups became a movement and youngsters could start building these things, and became easy to procure components from anywhere in the world to build these things and so on. All of that happened in the last 15 years.
Sure.
Before that, yes, we built systems, but with some difficulty. And so on. CDOT was a very big thing that happened in the government sector itself in 1984 or 3, when really a group of youngsters were encouraged to build a state-of-the-art switch. It was not a communication system; it was a switch, but an electronic switch. And when I returned to India and I went to CDOT, it was absolutely a mind-blowing experience, because all these youngsters below 25, 26, all sitting there working morning to night. Basically, what was done in CDOT was they were all youngsters. They could only be paid a certain amount, even compared to MNCs. Some MNCs had just started setting up in Bangalore. Even compared to them, they could not be paid as much. But what was done for them is, if you were in CDOT in the morning before breakfast, they would give you breakfast. If you were there in the night till dinner, they'd give you dinner. And if you came early or worked late, they would drop you and pick you up. I think those things they did, and that made all the difference. These kids were all living there, and they built that switch in 3 years. It was a fabulous team. And you see, many of those people, if you trace back what happened to all the people who were in CDOT in the first 5, 6, 7 years, they became industry leaders later. So,
my father's first job in 1968 was with Bharat Electronics. He describes a very similar work culture. Somebody says, "I want to build a radar," and they had the freedom to work on it and build it together. I think those were the foundations that are allowing us to think of 4G or 5G, our indigenous stack. What are the core elements that were missing that didn't allow us to do a 3G stack, but thanks to your efforts largely, we got to a 4G
so what
stack?
happened is, the exponential, explosive growth in technology, both in terms of the electronics, the semiconductors, and in terms of the complex systems, happened in the 90s and 2000. And we were late, right? As I told you, we started all this very late. So we missed the bus. So getting onto a bus late is very hard. So basically, subsequent to the capacity build up in the country, the barrier to entry is simply late arrival. It is not knowledge. All the barriers we've been fighting since then have been coming into a mature global industry in a very late. And the difference, we did that in automotive also. We came very late.
Yes.
Because India had these 3 cars for decades. And then you had. But the difference is the sheer bulk of a car and the logistical disadvantage, especially at the lower price end of the imports, because the prices go up when you have to bring a 1,000 kilo to 1,500 kilo, something from somewhere, especially from a wealthier country where everything costs more to do. You have an advantage even in those companies automatically coming here and setting up factories and so on. So you could get the auto industry sort of localized a little faster and better. Electronics is not like that.
And also the half-life problem that you talked about.
So everything
adds to it.
changes. So the cell phone, the smartphone today has about 1/10 the number of parts of a car. A car typically has 25,000-30,000 parts, and a smartphone has 2,500 to 3,000 parts. A smartphone may even, somewhat premium smartphone may even cost about 1/10 or 1/15 of a small car. But the point is, the smartphone weighs only 1,000th or less, 1/10,000th of a car. It's tiny, and the half-life of components in it is very small. So the manufacturing of a smartphone or a laptop or a tablet can be done pretty much anywhere in the world with no logistical implications. It can even be done at multiple places. It could even be shipped partly and finished at some other place. It doesn't matter, because these are all very small, very light things. One plane load would be worth so much. So basically, with that disadvantage and the speed at which technology is changing, it's very difficult for a late entrant. Very, very difficult. So, and then the WTO regulations also were brought in, which favored this kind of global manufacturing. So, the late 90s and early post this century, the difficulty that India has had in entering these fields, whether it's semiconductors, whether it's electronics manufacturing, has been compared to, say, automotive or anything else, has been that the late entry part. Now it's not the lack of knowledge. Well, in semiconductors, you might say there may be some lack of knowledge in the manufacturing processes. It's very sophisticated. But electronics, it's not that. The rest of electronics, today I don't think there's anything we can say that we don't know what's to be done. It's just that even if you know what's to be done, how do you now become competitive? How do you enter late? Okay. So to give an example, there are new technologies coming in these fields all the time. So now you have new technologies like gallium nitride semiconductors. You have technologies like silicon photonics. These are all very nascent stage. So these are areas where if you uh, participate at the state of the art along with the rest of the world now and enter, you'll be able to. And in fact, there are efforts in India in these things which are at par with the rest of the world. And if we have enough the required level of business risk taking ability, we can also, because you are entering at the ground floor.
Right. And also there's a physical manufacturing aspect and a physical product, but there is a very intensive and component of intellectual property in there, where again the late entrant disadvantage plays a role, but presumably one that we've now overcome over some, with concerted effort. What can a young engineer, looking to enter the world of communications, where can they draw confidence from that I can choose to now build a 40-year career in this space in India?
Well, for one thing, because this field has this natural tendency towards globalization. But I mean, globalization is, I don't mean to get into the arguments nowadays about whether globalization is dead or not. What I mean is the ease with which you can do different parts of the technology or the manufacturing or even the conceiving or the design in any part of the world, wherever it's done best, wherever it's suitable to you and so on, and put it all together.
Sure.
That is there for many things, but it's really very sort of intrinsic to this miniaturized electronics field. So I would say that given that is the case, it's also true that a lot of the companies in the world that are of originating from other countries, which are leaders in their fields, all of them are now moving substantial part of their R&D, even their intellectual property development to India because of the reasons being availability of talent, population, lower cost, all these things.
Sure.
So the so-called GCCs, as we talk about.
Yeah.
In fact, the biggest growth sector in India in terms of employment now is not the IT sector; it's the GCC sector. So GCCs come with all sorts of flavors, but all the time the quality of work, the intensity of work, and the level of the work going on in GCCs in India is growing. So I would say, from a student's point of view, from a career point of view, a lot of the value chain in electronics, starting from even if you're even a semiconductor company, we run a GCC here. We may not make the machines in India, we may not do the fabrication of the chips in India, but the companies that make those machines are all running GCCs here and developing parts of the thing here. Of course, the question of who owns that intellectual property is different. It may therefore belong to somebody else, but from a student's point of view, the ability to participate in that value chain is improving every day.
I've always believed there are two partners to the, two holders of the intellectual property. One is your employer that holds, quote unquote, the patent, but it's also resident in the individual that did the work. So
that is happening already. A good part of for more than a decade or two now, a lot of the a lot of the chips that are now sold by the leading semiconductor manufacturers in the world are designed completely from India. And in fact, some of them, the business is owned by the Indian arm of the MNC. Okay. When I say owning a business is different from doing the design. That means who takes the decision to invest in that, reaps the benefit of which business unit reaps the benefit of that. That also is now an Indian business of the Indian business unit of that company. So full value chain is actually resident in India in many cases, and many more cases than not. Still, I would say the full value chain doesn't reside here, but it's increasing, and I would think therefore that the opportunity wise from an individual's point of view, I think is probably never been better than it is today in this field.
And this is true with broadly the space of consumer electronics,
everything.
Right?
Probably less in military electronics, but
Sure.
you'll be surprised at the amount, because with more care to make sure that their intellectual property is protected and their security is protected. Many companies actually get a lot of the intellectual property work done, even for defense electronics in India. But they do it very, very carefully. They are experts at it.
Sure. Let's switch gears and talk of electric vehicles. Electric vehicle is today a very sophisticated electronic system on wheels. Where is India on the electronics and the electrical engineering aspects of EVs?
Actually, even an ICE vehicle, even an internal combustion engine vehicle today is sophisticated electronics.
Sure.
Okay. I mean, the only major difference between the two is that in the ICE vehicle of today, the mechanical, electromechanical, or mechanical, propulsion system is controlled by very sophisticated electronics. Whereas the electrical propulsion system is controlled by very sophisticated electronics in the case of electric vehicle. Otherwise, the rest of the electronics is as sophisticated now in the two. Okay. So I would say broadly, electronics and intelligent software-driven electronics is entering everything, right? From washing machines to cars to everything. And therefore, all these systems have higher part of their values now in the electronics and in the software and in the AI that's used in those machines increasingly. That is one phenomenon that's happening, whether it's ICE, ADAS 2,
Sure.
is just electronics and in software, sensors and so on. The electric vehicle has another aspect to it, and that is the other part of electrical engineering, which was probably dominant before the electronics revolution, and that is the electromechanical part of it, the energy transfer, machines. When I joined as a student in the electrical engineering department in IIT Madras, it was the machine section that was larger and which had many of the stalwarts of the department. Then during my career as a faculty member here, that declined because nobody would go into that and so on. Of course, I had a half suspicion even in those days that it will bounce back, and that's what happened with the return of electric propulsion in vehicles and everything. Now it'll come to planes and everything. So it's come back. But the point is, machines which are actually deal with the conversion of electrical to mechanical and vice versa energy have always been important, because that is the heart of the electrical power system that drives our lives, and now of all the propulsion systems. So this area, which had seen a sort of a decline, is now back with full force. And obviously, people have taken time to figure out that this is now a very important area, and students are not yet flocking back to the extent they should. Many institutions are bereft of faculty in those areas. They have to build them back. So that's a problem. But the real challenge there is, compared to the machines that were there in the 50s and 60s, which drive all our power stations and everything, and our motors, the thing is, if you look at electronics today, if you look at phones today and so on and marvel at them, those machines are marvels. I mean, apart from the human body, which works for 70, 80 years without too much of a problem, the only other machine that I know that works without any problem is the electric fan. Everything else requires service engineering and visits to the service shop and all that. But this fan that you switch on in your home, how many of you think about it, that you just keep switching it on, and you see fans that are 60 years old, 50 years old in old homes that are still working? And except for
it's the ball bearing that could go bad.
Even that, they've mastered it. I mean, I've never seen, no homeowner has problem with his fans. Correct. They have problems with everything else.
Correct.
Right? So the electrical machine, the synchronous machine, these are all they run on alternating energy, AC current. It's a marvel of engineering. Rely from reliability, and it just runs. It's very simple in its construction. From that high point, and everything was built on that. Now there is a complete revisit, because what has happened is this has become, if you are going to use if you're going to use electrical propulsion rather than mechanical propulsion, if you're going to use motors in cars and so on, you want to build them now as well as you can. And unlike a fan, which sort of has to work at pretty much at one speed, you can change speeds, but it's not changing all the time. There's no requirement that it should also produce torque. Now when you're doing for propulsion, you have multiple requirements which are against each other in terms of what you need to do, and you want to do it well, and you want to do it efficiently and so on. And so I think all of these designs are being revisited using all the new tools that are available, computational tools for design, much more precision. So all these have to do with the strength of the magnetic field, have to do with rare earths, have to do with the gap, how minimally you can make it. So it's become a very multidisciplinary area where I think people who have a good understanding of the state of the art in bearings, in control, in design, in numerical, electromagnetics, everything will come together. And the power, the thing is to, when these machines want to do different things, go from high torque to high power mode in a jiffy, it's electrical machine. So somewhere the electrical signal also has to go from one end to the one type of signal to another. So the electronics that can also withstand these quick changes also is, that's called power electronics.
Yes.
That is also new. That's very different from the low power electronics that goes into smartphones and stuff. So the devices for that are very different. The kind of materials that are used to build the devices are different. You have gallium nitride, you have all these other things. So silicon carbide and so on. So all of these are becoming new technologies that are coming in. I don't think the required manpower is there for these areas the way it's there for conventional electronics.
Sure.
This is going to be
Is that you say globally or
I
only
would say
within?
globally to some extent, and
Very nice.
because academic institutions, shed areas where they can't get faculty or which are not so hot, and then getting back, it's all slow process.
Sure.
I think in countries like China, they react much faster to these things. It's overall, I would say, in Europe, they don't shed things too easily, so they're able to bounce back. But America is taking its own time. Many universities in America don't even teach these things.
Correct.
And in India also, we are not doing as bad as I thought we might. We are bouncing back. But so this is an area where I think there's going to be a lot more possibilities for people to do. It's going to be very multidisciplinary, because I think, and I don't think even I don't know how, about China much, but in many parts of the world, putting the teams together from all these disciplines so that you can really pull off the best design, I don't think is really happening. Because these, if you really want to build these cut machines that can, work at the best way from high torque to high power situation and so on. I mean, anybody who does something with a better material, with a lower gap, better bearings will all matter.
Sure.
Few percentages will matter. And now we are back to bulk and weight and so on. So this is not something that can be easily done in 5 countries. They say a smartphone travels so many times before it's finally done, right?
Sure.
From between countries. I don't think this is a technology that's going to allow that. So there's going to be a lot of localization possibilities.
Very nice.
I think this is an area where a lot more people should get in, both at the student level and the faculty level and the engineering level.
I think automotive applications of power electronics and machines is sort of tangible here and now.
It's not just automotive. I
Just
would say
drones.
even in the renewable energy, the grid.
Yeah.
Because the same thing is happening, right? You're having sources of energy of different types. You're having very, very gentle sources of energy like solar power, which cannot change very quickly. Then you have wind, which you could have gus. Then you could have stuff which you can control like hydro, which you can turn on and off. So how do you put all this together? How do you manage rapidly fluctuating energy sources and energy demand?
Yeah.
So this is also an area so there are lots of possibilities. It's not just in automotive.
So in some sense, while communications engineering has driven doubly in the last 20, 30 years, driven electronics or driven motors and machines, the power grid, are also areas where there are careers waiting.
And the thing is, computation is strides across all these.
Yes.
Computation is at the heart of communications, and computation is going to be at the heart of all these things also. So
that's
compute electronics is common to all of this, and that's another thing that's going to drive.
So if you look at, let's say, computing, as you said, let's talk a little bit about that. We talked CPUs for many, many decades, and today, you can't do serious compute without GPU. So somebody fortuitously found an application for what was just a picture shower in some sense. These sorts of fortuitous discoveries, I don't think happen by serendipity alone. There is a certain engineering and a thought process that goes into that. How can a young student today be ready or prepare themselves to sort of be the recipient of a serendipitous opportunity like this?
Yeah. See, I think if you look into these things, at one level, what happened to the GPU is not. I mean, it is very clear from the mathematics that you develop for doing AI and other things that you need vector processors.
Sure.
Okay. You need to process matrices, vectors, and so on. The question is, when you take the investment required in electronics to build a new engine, new machine, computing machine is huge. So for somebody to have proposed that we need to build a new type of processor, which will be much more suited to AI when AI appeared to become feasible in terms of the computational requirements. Because AI, I remember exploring with a student in '93 the use of AI for some biomedical thing.
Yes.
And we gave it up because saying with the compute required, we can only do toy problems. And it's not going to solve any real problem. So we gave it up. So actually, it is not that idea of AI has not been around. So it's just that the level of compute by which you can do really useful things became feasible only in the last 10 years. Now, when that happens, and you as a builder of AI systems wants a new type of compute engine, the amount of investment required to build that from a chip angle is so high, you will not get very far unless you are part of some big investing chain. Okay. So what happens is, if it turned out as it did, that something built for something else was repurposed, possible,
Yes.
you could do it. And that's how the GPU came. I'm not an expert in this. It may well happen that the particular architecture that's being used today in the GPU can be improved upon tremendously or significantly. But then the investment required for a new machine that does better than the GPU is very high. And the other thing that has happened is when the GPU was repurposed like this, a huge base of software was developed, which takes a lot of effort to do around that engine, which helps you do all this. Now that has become a barrier to entry. Even if you build a new compute engine which is better than the GPU for this AI application, you may not have the kind of software base developed for it on day one that they have. So getting people to move from that is very difficult. So the software that goes with the GPU today itself is now a barrier to entry. It's just like the way, is it that nobody could design something better than the x86 family? Probably not. Probably somebody could have. But the huge software base, the drivers itself,
Correct.
available for the x86 is just so large that nobody's going to move. So that kind of thing is also there. It's not necessarily the best thing available or that could be made, but it's the best whole ecosystem that's available that is difficult to replace. So when you say serendipitously, what happens is, it's like saying that I've found a new way to, some new propulsion technology. If to build the ideal machine engine for that is very difficult. But hey, you know what? I can take a small plain aero engine and I can repurpose it and do it and reasonably well. Then you do that and you get a shot at opening up that market. So that is the serendipitous part. But the person who has to do that, the group that has to do that, has to have a good enough grasp of the fundamentals of what they are building to know that the other thing that is being repurposed is a reasonably good approximation. So I would say, like in all things, getting to the people who have to break new ground have to know that fundamental.
We talked of GPU and CPU compute. AI is taking the world by storm, and we are all first person. We have first person accounts of what it is doing for each of us. In your own fields, in communications and broadly in electrical engineering, where do you see AI coming to help, and what could a young engineer do to equip themselves? I want to add one thought. I remember you when we were discussing faculty recruitment. You had a vision that every department should have domain AI capability. Elaborate on that, please, and help us understand where AI is taking the
So
lead.
AI is not that new, as I think I mentioned it a little while ago, that AI has been around. The techniques of AI many techniques of AI have been around for many decades. Many of them are based on very solid optimization methodology that has been developed in mathematics, in applied mathematics, in engineering, and so on. The big difference is, the method we all use as engineers to use these engineering is all about optimization, how to get something done with lower energy, lesser material, faster, better, so on. The way we tried to optimize a system that we were designing is to build a model for it. Real life systems follow models to some degree because the laws of nature don't necessarily follow the models that we have, or we don't have good enough models for them. Or the systems that we build don't necessarily follow the models that we would like them to follow. Then we manage those models. We put in factors of safety. We hope that things will work. That's generally how aeroplanes are built. Buildings are designed. You don't know exactly too much about the soil that you're building the building on. You have to put in factors of safety. You don't know too much about what the wind is going to be. You have some data on wind and so on. So you build these things. All engineers do this. Now the point is what is happening with the simultaneous ascendance of compute capability and sensing capability. So the other thing that's happened with all these electronics in combination with various other devices that leverage various other physical phenomena is that we are building more and more versatile sensors that can measure all kinds of things. The physical parameters like temperature and pressure and all these things are obvious ones, but there are so many things we measure in real time. And associated with that, the communications capability that has been built with the same electronics. So combination of electronics and sensing, materials and so on gives you sensors. Then the ability to communicate the measurements over distances instantaneously is built by the same electronics, miniaturized electronics with communications.
Sure.
So you have all these sensors that you can leave inside pillars, in buildings, on under overpasses, and on your phones, and everywhere, and on the human body. So all these sensors are collecting data, and now what is happening is, or you have a sensor on the wrist of a operator who's doing grinding in a factory using a grinding wheel. You are constantly picking up how much pressure is being applied, how the grinding wheel is responding, and so on. All of this can be picked up. So you've got now 1,000 eyes and ears watching and hearing, sensing what's going on in a system where you have some model which is approximate. Now the question is, how can you use all this data, both past data and real-time data, to along with the model to do a better job of what you are trying to do as an engineer, and let the compute engine figure out what the underlying model is. You don't even have to know it. So that is what AI is coming to in everything, right? So the ability to this is what a human being would do with some limited measured data earlier, and we call that experience. Now you can do it with limited. Even now there are many situations where you have only limited data, but in many situations you have more data, and therefore these engines compute engines that actually figure out, AI engines that actually figure out how to optimize it, or what may happen in the future, when it might fail, and so on, are becoming better and better, and newer such computer AI engines are being brought into play every day. So AI is, and that's why people say AI will enter everything, right? Because wherever you can do better at whatever you wanted to optimize by collecting real-time data, by looking at past data, and changing the behavior of whatever your system that you're engineering to do whatever you want to do better, consume less energy, consume less material, have less breakdowns, whatever it is. I think, or drive the car on its own. I think they are going to come in. So that's really what.
But it is not an AI engineer, but it's an electrical engineer with AI knowledge that would be more valuable.
Yeah, I think the one aspect of this is knowing this new technique which allows machines to look at data and learn how to interpret the data. It's not that we are telling it, plug this formula in data into this formula and do. That's different. It's actually figuring out the formula, right, in its own way. Not even printing a formula, right? So you have to learn how to. It's a new animal that's come out. You have to learn how to control it, how to make it do what you want, right? So I think of it as that now extinct fellow who used to do this show on the road with the monkey, right? So if you were suddenly handed over that monkey, which with proper training can be made to do things that you can predictably ask it to do.
Sure.
You have to learn how to do that, right? You have to learn how to make that monkey do those things, or maybe do something not yet done before and learn those. Only then you can get it to do things, right? So I think people have to invest in the time and energy to learn about this AI. But yes, it is in the combination of that application of that AI, or the combination of AI in various domains, where it's going to have the maximum.
Sure.
And it can do some things well, it can't do some things as well at any given point in time. It may do some things better tomorrow as people learn how to make it do things. But therefore, knowing what it does well, knowing what it doesn't do that well, is also very important in finally putting out a useful system today at any point in time. Because if you put out something which claims that which don't stand up to scrutiny, then people are going to get upset. So all of that is important. So I think there's a huge scope for people to master this new capability, even as it's improving every day, and bring it to play in many things.
In different domains. Let's go back to electronics and talk of India's semiconductor ambitions. You led the thought revolution to tell the governments of the time and the people largely also that we had missed a bus, and that there was time, it's about time we realized how to not miss the future buses. Where do you see India's semiconductor ambitions today? I mean, the end-to-end value chain from IP creation to fabrication. And where do you see us 10 years from now?
Well, I don't think I'm needed to tell the government or anybody. I think everybody realizes that we missed many buses. It's not that it's not realized. In fact, this, especially in semiconductors, this realization, because we were actually not too far from being in the ground floor even as late as 1990. We actually had a semiconductor manufacturing capability in Bharat Electronics to make transistors, which was shut down. This was the first era. Wow. 1960s, 70s, right? In fact, when I was a student, the transistors that we bought in the market to do our electronics lab were all Bharat Electronics transistors, not imported transistors.
In fact, as a little bit of an aside, there's a book that Chris has written, Chris Gopalakrishnan, in which he talks of India, Homi Bhabha, having led a team to build a supercomputer in India.
Maybe, yeah. I don't know about it, but yes. So I think that, there was nothing in the world other than transistors in 1960s, and we were building them.
Yeah.
Then when the first chips came in the 70s, we had decided to quit that. But then we came back with the semiconductor complex in Chandigarh, and we had a pretty, not too, reasonably state-of-the-art capability. We sort of let that slip in the 80s, and then we upgraded it even in the 90s to a state-of-the-art capability with Tower Electronics as the technologies provider. Then there was a fire and we lost everything. And then somewhere they took a decision that, we can't get into this. We should focus on our strength. There was this alternative theory in economics that you focus on your strength and so on. And we stopped. And when we stopped, that was Moore's law was in full play. Every 18 months, things were doubling in capability. And several exponents, doublings we missed. And the barrier to entry, by 2010, 12, even before that, maybe the country was clear that we can't afford not to be in this. There are too many vulnerabilities from a national security angle, from a trade angle, and so on. So we wanted to, but it became harder. And the reason it became very hard is you can sort of measure the level of difficulty in terms of simply this one parameter that people throw about even in the late literature, which is the so-called feature size, nanometer. So the feature size is sort of the size at which you etch individual electronic components in the chip. So when we tried to come up to the state-of-the-art in Chandigarh in the early 90s, the feature size had just come to below 1 micron. In fact, I remember when we were doing our wireless local loop system, 1 micron barrier was crossed and was announced in a big way, and 1000 nanometer. Okay, and when Chandigarh was rebuilt, it was 180 nanometer, which was considered state of the art. And but to give you an idea, 180 nanometer products are still growing in volume. Many things can be built very well with 180 nanometer. You don't need lower feature sizes, so it's still growing. It's not a business that companies are willing to give up. Okay, so we actually had started with that at the right time, but we still didn't pursue it. Then it went to 90, then 45, then 28, and so on. And now it's down to 3 nanometer. Right. So every one of those halving, the barrier went up. Right, and the barrier went up because of two things. One is the machines that you need to do these become more and more expensive. So you have to run this factory more efficiently to recover the investment. And beyond, when it went below 28 nanometer, and particularly it went to 14 and below, even the nature of the technology machines changed. The physics, underlying physics, which was at play to do these things, what you do those machines itself changed. And even the getting the yields in the factory with those machines became also part of the IP. It's not just putting the machines, running it all as per the manuals, right? You had to actually learn things on them. So the barriers became harder. And the investments required to get such a factory going became higher. So the risk-taking required became higher. So it became harder to get these investors who take the risk to set up these factories. So by the time we've actually come to the point now where we are setting up our first big fab in India with 45 nanometer feature size, which can be fairly straightforward way reduced to 28 or 22 nanometer. Then to go to 14 is another big step. By the time we've done that, it's became almost, there's only one that's been set up now. Somebody has found and the government has had to subsidize it to more than 50-60% for somebody to take the risk. Okay, that's what has happened, and yet so that's really the danger in not getting in at the ground floor. Imagine, we are very strong even in IT services. To take an example where we are in the driving seat, IT services is a little bit like setting up semiconductor factories in the 90s. And, why did the countries that make the machines allow others to set up the semiconductor factories? Because they felt that it's not a very important part of the value chain. And in fact, they are selling the machines upfront. They are recovering their investment upfront. Let somebody else, churn out the chips. Why should we do it? That's how it was done because the Americans are pretty much behind the technology for all this. So why did they do that? Because that's what they. Then when the technology started becoming better and better, then the actual running of those machines, the actual getting the yields became important. So some of the IP started residing in those companies, and that's now they're worried about that. They suddenly woken up to that, Americans and so on. But if you take um, uh, countries like India, we are such a huge consumer, and there's a national security angle to this. The same technologies are vital for in defense and so on, or even denial can lead to a problem. So we want to have our own supply chains, and then we want to set up these factories. And now it's very hard to get the investors to take the risk. It's very hard because it has to be commercially viable. And then even if you do it, even we get to the point, let's say we do 14 nanometer, then 7 nanometer, 3 nanometer. Remember that all these machines still all over the world come from a very few vendors, and they control the switch. So there is still a huge, of course, as I said, many of them have GCs in India and so on, but that's a different matter, question of who controls the switch. So this is a technology in which still I would say there are very, very huge barriers. But you have to have, you got to just like in electronics manufacturing. If you don't assemble phones, some people used to say, "Oh, what's the use? It's very low value add. It's women and men sitting at benches putting things together." But if you don't even do that, how can you hope to even replace some components in it? Yes. Right? If somebody else is doing it, why would he take your component? Right? So you've got to do everything. Right? Then only you can hope to. Maybe at some stage we'll make a machine that does something better in that. But if you don't do it, if you don't run those machines, how are you going to even figure out what's a better machine?
Now that we've decided that this is an area that India is going to invest in for various reasons that you just described, these are not jobs that a B Tech or a BE student graduating fresh off college can get into. They're very sophisticated.
Well,
how do you equip yourself to get into this line of work?
So you'd be surprised that actually one of the barriers that was discussed, because I was part of those committee meetings, one of the barriers that was discussed to bringing a semiconductor fab into India, the machines anyway are going to come from somewhere, and you have to set up this line. You got to make sure the yields are good enough commercially that you can compete with the other fabs in the world and hold your own, even if you are having a market in India and so on. The point is, a lot of the people who need to be on the shop floor are not necessarily, are even probably well-trained technicians and engineers. And we actually don't even have the academic infrastructure to have well-trained technicians or even shop floor engineers. The IIT output, for example, is not suitable in large numbers for this. So one of the things that was pointed out to us by the leading fab potential partners who were going to set this up was, where are the engineers? I can't bring them from Taiwan.
Yeah.
Okay, and we didn't have them. And we still don't have them. So actually right now there are some programs that are being run by some colleges, not the IITs, where students are actually being trained 6 months here and they're being sent to Taiwan for the rest of the training. So it's not true that we have though we produce so many engineers and so on. And this area doesn't require zillions, lots of people the way manufacturing does. But even the numbers that are required, we don't produce them. So there are many. The entire value chain in the semiconductor manufacturing. We have a huge hole, and we are now having to fill it. So if you look at the first fab that's being set up there, I read somewhere that something like 60-70 of the top management is all expats who have been brought in, because we just didn't have it. But I would say even the shop floor people are all being trained now by special programs. They just can't be, you can't hire a staffing company and get them off the Indian firmament. It's not going to happen.
On a related note, when IIT Madras was set up, 60-70% plus of the professors were probably expats.
So it can be done, but it needs, governments are not very good at this kind of very strategic plugging holes and getting things done and so on. So, but unfortunately, Semiconductor technology is one area where it requires that kind of attention to be paid if we have to get it off the ground.
Let's zoom out a little and talk about careers broadly. This is now going beyond electrical engineering. When students, their parents, and a small group of well wishers sit down to try to figure out what a high school graduate should be doing with their life, there are very limited parameters that they seem to factor into their decision. I've seen even so-called educated people, and the two words I hear bandied around quite a bit: scope and package. Is there scope in this discipline, and what is the package? I feel very sad for that discourse. Help us understand what is a more knowledgeable framework in which parents, their well wishers, can really think through and do what is right for the country and for themselves, of course.
Well, it's understandable because you have the largest young population in the world trying
Yeah.
to find careers for themselves. On the other hand, it's not a very bleak situation because you also know that in the next 10 years, we are going to go as a country from 4 trillion to 8 trillion and beyond. So, where is all that 4 trillion is going to come from? It's going to come from these people. Therefore, and then, so 16 trillion, 20 years from now. So, the point is, everybody knows that is there. Everybody knows these people are there, but each individual wants to minimize the risk and maximize the possibility of getting it right. It's understandable. Okay. The thing is, scope is what? So, first of all, I think people know whether you are doing traditional padashala or whether you are doing modern engineering, education or whatever. People know that if you learn some things, skills or knowledge at a fundamental level, that's where it pays off. Everybody knows that. But everybody also knows that the opportunity, in a large pool like this, where people are picking individuals off the internet or whatever, of staffing companies and so on, not necessarily based on individual knowledge of the potential hire. People also know that having making the right noises at the entry stage can be important. So that's why they worry about what branch to take, what
Yes.
to know, and so on, even if it's not at a fundamental level. Okay, so that's okay. It's understandable. And scope is related to, since AI, for example, is entering everything. It's a no-brainer that if you learn the basics of AI, you have the maximum scope.
Correct.
Okay, if you learn something, let us say specific to numerical electromagnetics, you have a scope in companies that are building the latest motors and so on, generators, but that's all, not in everything, right? So that is an issue. You want to maximize scope. You want to learn things which are used across the board. Okay, every human being has to eat, so obviously cooking always has scope. Food services always have scope, right? So it's not going to go away until food becomes unimportant, right? So that's not like that. That's also true. And I would say, if you are not fortunate to get, if you're not that fortunate to get a higher quality education, if your education is of middling quality, then the pay package, the opportunities, the first opportunity for a job, because the rest of the learning happens on the job.
Yeah.
But the first opportunity is a mixture of being at the right place, right time, and so on, and the way the current situation in the industry and so on. So, uh, you know, the packages, obviously, when you take people who are not that well trained or that well at the entry level, the packages are not that high, and many people who look for their first job who come from families may be having financial stress also. So it's understandable why they worry about package. So having said that, therefore, I think a lot of people have a genuine reason to worry about scope and package. But having said that, let me start at the other end.
Yeah.
I think in places like the best education institutions, I don't necessarily mean the IITs, any institution that does a good job of education. It could be a degree college also. You know the ones they have. Even now, NIRF does a pretty good job of at least statistics. They may miss one or two here and there, but statistically, I think they capture the leading institutions in all disciplines. And the students of those colleges and those IITs and those institutions, medical colleges, everything get placed very easily because everybody knows, who's hiring also knows that these people are very good. They are capable of learning even if they don't know something today. So something that you need today. So they all get picked up. And if you look at the median salaries in their placement data, it's all pretty good, right? But there are always these outliers that who are getting picked up at fancy salaries in those places. So there is one set of people who are always aiming for those outliers, and without realizing that no matter what, very few people are going to get those, right? And if you actually study who gets those, it has very little to do with any predictability about that individual, either capability wise. Statistically, yes, some of them are shining. They are shining in their academics, they're shining in their, even in the 2-3 years internships and so on. But, and some of them will probably, therefore, uh, there's some predictability that they might have capabilities which are above the ordinary. But in many cases, that is statistically, that's not so. Statistically, I think many of them are not predictable. So I think the first thing is students and parents should realize that if your aim is for that, and no harm in wishing that, but I think it's not a predictable thing that I can actually work for it. If it happens, good. Doesn't happen, you should be happy, because anyway, whatever the rest of it is not bad. The median is not bad. So it's more important to worry about learning and working in things that you like to do, because your ability to learning is not going to end in. I said the same thing to some students this morning in class who asked. The course got over. Some of them got around asking these things. So I think the process of learning is not going to end. Hardly the beginning in college. You have to continue learning on the job. It takes 10-12 years minimum to become good at anything. So you have to worry about whether the where you're working is interesting enough for you and gives you the opportunity to learn and grow. Unless you're getting up every morning raring to go and continue the learning process, it's going to be very, very difficult. So as long as the package is good enough to live comfortably, and so in these institutions where the median itself is quite good, I think it's advisable for people to learn not to target the outliers. Just if it happens to you, you're one of the lucky ones. If it doesn't happen to you, fine. You really can't predict for it. Okay, plan for it. And I think if you look at the people who have either had a great startup, with a grand IPO, or even a great job in one of the top companies in the world, if they are honest, many of them will tell you that they really don't know what it is about them that got them that. Okay, so I think the rest, for people who are having to have to settle for a more middling education and so on, which doesn't necessarily prepare them for the world outside, where more of the learning is going to happen on the job than in the degree. Okay, that's all it is, right? So I know so many people who are after 20 years no different from the one who came from an IIT or something, but they did all their learning after, most good part of their learning afterwards. Now I'm not saying they didn't learn anything in college. That's not true. Subject wise they have learned some things, but more than beyond the subject, the learning of the other aspects of life skills are probably the opportunity is probably not very different depending on where you go. So many of them have learned those in those other colleges. I don't want to belittle the contribution of those colleges, but where the academic learning or the knowledge learning itself is of a more middling level, I think the point is they should, I think it's understandable why they worry about the package and the scope. It's understandable that they want to minimize the risks by going for learning those skills in those 4 years, or getting that knowledge in those 4 years that has a maximum scope. So AI, for example, would be a candidate today. A circuit branches were the candidate 15-20 years ago. It's understandable. But I would say that there's so much evidence that if you didn't get an opportunity to learn those also, it doesn't matter. You will, in a growing economy like India, where the next 4 trillion and the next 8 trillion per year are going to be 12 trillion are going to be added in the next 10 and 20 years. I think even niche areas, people are going to find employment. It's more important to make sure that you are good at it. I mean, let's say you are a mechanical engineer and you specialize on, on projectile motion and bulletproof type of technology, how to build bulletproof vests, how to build things that can withstand explosion, so on. Even that will have a reasonable, the number of people needed in the country may be 100 or 200, but there are agencies, there are labs, there are companies that need to do that.
Yeah.
So that way I would say even very niche areas there's employment opportunities. Obviously the scope is very little. You can count on the finger, when your fingers are one palm, which companies can recruit you. But where will they go? They need people also.
Yes.
So they will have to come to you. So I think it's possible, but so I would not blame people for looking at scope. I would not blame a lot of people for looking at package. It may be important even at the entry level for some families, but I would say the moment you get into the frame where your package is decent, but you're constantly looking at people who have got these fancy things, I think that's where you should stop.
Wonderful. Thank you so much. You've done a fantastic job of parsing this. So the where India is today is where scope and package are more or less in correlation. I think we will see niche professions version where the scope could be limited, but the package would still be decent. Because, and the second point you made, that on-job learning is a great value add to
It is
to
the
an
main thing.
individual.
You
It is
can't
the
learn
main thing.
anything in 4 years or 6 years anyway.
Exactly. So, in that sense, so I think as we look to the next, next extra trillion that we will add to our GDP, they will all be, there's also a breadth of professions that will become available. And so I think thank you so much for that bringing that extra perspective. And in all of this, for the on-job learning to really progress for the benefit of the engineer and the student, a certain amount of passion for that discipline.
Absolutely. You can't
is
learn
important.
without wanting to learn.
Right. So, and on-job learning has another unique aspect that an employer is paying you while you are learning. So they also have a vested interest to make sure
So you
you're
also have to
learning.
learn values. You have to learn to, if you've got something out of somebody or some company, you have to learn that you owe something back. All these things are important.
Thank you so much. This has been a wonderful conversation.
Thank you.
This is, I'm sure, will be archived for future use, and I really want to thank you for making the time to come
Thank
on
you.
this podcast.
Thank you very much. Thank you for having me on your show.
Thank you very much, Professor Bhaskar, for a very, very insightful conversation. This podcast summarized for all of us all of the exciting things that are happening in the wider world of electrical engineering, the whole semiconductor revolution that India is now a partner to, uh, is going to change many different careers, is going to give birth to many different new careers in India. The electric vehicle revolution, and even the re-engineering or the reinvention of the internal combustion engine are all directions where electrical engineers have a key role to play. Um, I hope you picked up the different directions in which engineering largely and electrical engineering in particular is going. And I hope you will use this information to make more informed choices. Our objective is to bring you future simplified. Thank you all for listening. Until the next podcast, be well, do good, and keep in touch.